Hello, welcome to another Stat 510 video. In this video, we're going to discuss Bayesian inference. This will also sort of start to be us looking at the bigger picture and summarizing the class as a whole, because Bayesian inference is going to stand in contrast to everything we've done so far. So, we've kind of repeatedly referred to this picture as what we've been doing in this class. So the first few weeks we said, okay, here's a known population distribution or a data generating process, whatever you want to call it, and we can sort of ask probability questions about potential data being generated. We can say, what's the probability that we observe blank, and those are probability type questions. Okay, but then the back half of the course and the focus of our course is to do the opposite thing, which is to say, okay, we have some data, but what does that tell us about the true state of nature that is the underlying population or data generating process, whatever you want to call it? So we've needed to use what we learned about probability to do that, but we've used it in a very particular way. And that's sort of what we're going to really highlight in this video as we introduce Bayesian inference. So first, I want to sort of refresh our mind about probability. And I know I'm covering some of it up with a camera, but it's not important to actually see what's behind that. What's important is to note that what we have here are the axioms of probability. So basically, this defines probability as a set function, basically. Like things go into this function, probabilities get spit out. But the important thing to remember here is that this is very much detached from reality or practical application. In a lot of ways, these are just, you could think of this as arbitrary axioms. And then, people that are interested in math, so probabilists or mathematicians, they derive a bunch of new things based off of this. And that is, a lot of what is done in probability theory. And that is, in my opinion, largely mathematics. We're not doing inference here. We're only sort of looking at the one direction here, which is talking about probability. And I mention this because while we as sort of humans interacting in the world, we kind of have some built-in notion about what probability is and what it means, but these axioms here, they don't care about that. These are just cold, detached rules that we must follow to use probability theory in our applications, but they make no claims about what probability is or what it means. They're just arbitrary rules. So I guess what I'm trying to say is that probability kind of has different aspects to it. There's the theory aspect, and then there's the application. So the theory, is more or less all derived from those rules or axioms, whatever you want to call it, and the manipulation of them and the derivation of new rules based on the axioms. That is mathematics, in my opinion. In particular, probability theory, but that is. A lot of statisticians engage in that, but that is, in my opinion, mathematics. Now, on the more application side of things, now we must follow the rules of probability, but we're also interested in, well, what is probability? What does it mean? How do we interpret these things? So what a probability is and how we interpret that is it's paramount to application, because if it doesn't mean anything, how can we apply it to anything? And this, in my opinion, is where statistics comes in. Because statistics, while yes, a lot of it can be, a lot of what we've done in this class is very mathematical, but at the end of the day, statistics is meant to be applied to data that was generated from the world to help us learn things about the world. So how we are interpreting those probabilities really matters. And so we're going to talk about that a lot in this video. So until today, as you're watching this video, everything we've done in this class would fall under the category of frequentist statistics, up to and including our use of Bayes' theorem. That might seem odd because where we're going is something called Bayesian statistics, which stands in contrast to frequentist statistics. Again, we've seen Bayes' theorem, but Bayes' theorem, actually, is that the next slide? No, it's not. Bayes' theorem can be derived from these rules. Bayes' theorem is not something that belongs to one camp or the other, frequentist or Bayesian. Both use it, and Bayes' theorem is just it gets derived from these rules. Bayes' theorem, again, until we add some interpretations to things, it's just a cold, hard mathematical fact. Okay, but so what is the difference between frequentist statistics and Bayesian statistics? And it largely has to do with how they interpret what a probability is. So frequentist statistics is often considered the sort of like classical approach. It's the one that most textbooks take sort of by default, and then Bayesianism is the side effect. There are outliers that do Bayesian first, but for the most part, the first time you see statistics, you see frequentist statistics. And in frequentist statistics, the way we interpret probabilities is we say, okay, suppose that we reran this experiment an infinite number of times. How often does the thing we're interested in happen divided by how many trials you did? For example, I have this silver dollar here. It's a coin with a heads and a tails. And we could say, well, what's the probability that I flip this coin and it turns up heads? Well, in frequentist thinking, in our mind, that probability is, well, if we flip this coin more, approaching infinite number of times, the proportion of times it comes up heads, that is the probability. So in frequentist statistics, it's all about relative frequencies. So that's how we interpret probability in frequentist statistics. And then the other aspects of it are parameters are fixed but unknown constants. So for example, the probability that this coin comes up heads, that is a fixed unknown parameter. We don't know what it is, but it is fixed. We might assume it's 0.5, but we don't know. It is whatever would happen if we flip the coin an infinite number of times, the relative proportion of times it comes head. That's the value of that parameter. We just don't know what it is. And we would take samples to try to figure that out. And so often in frequency statistics, we like methods that have these well-defined long-run frequency properties. Think of a confidence interval, right? So in frequency statistics, we speak of a confidence interval. When we say a 95% confidence interval, that does not mean, oh, this confidence interval has a 95% chance to cover the true value of the parameter. That's not what it means. What it means is that if we use this method of creating a confidence interval in appropriate situations repeatedly, 95% of those will cover the true value. So the frequency here is about the method, not about the particular interval. So that's and that's very confusing when you're first learning statistics. So the contrast to this, Bayesian statistics. So in Bayesianism, probabilities are no longer these things that have to be these relative frequencies if you repeat something. It's instead simply a degree of belief. And in a lot of ways, folks might say, well, this is subjective. Whereas this back here, the frequentist approach, is objective. That's true-ish. There are ways of doing what's called objective Bayes, but we're not going to get into that. But so let's think about why this might be necessary. So thinking back to frequentist statistics, I think the thought experiment of me flipping this coin an infinite number of times is not hard to fathom, right? I could, lock myself in this room and just flip this coin until the end of the time. And really, I don't need to do an infinite number of times. After a large number of times, I'm going to be close to the answer. And we kind of all understand that, right? But in our day-to-day lives, we often sort of associate sort of degrees of belief with various events. For example, one of the most studied events in recent history was the 2020 U.S. presidential election, right? So a question that probably got asked a lot is, what is the probability that Joseph R. Biden wins the election and becomes the president, right? So all sorts of people will tell you a probability for that event. However, let's try to think about this like a frequentist, right? So a frequentist would have to say, okay, so if we reran the 2020 U.S. presidential election an infinite number of times, which I don't think anyone wants to do, what proportion of the time does Biden win those? And just right away, it's a very weird thought experiment, right? So you either need to imagine like some sort of time machine where you can go back and keep redoing it because there's only one Earth, and this only happens one time, or you need to buy into some sort of like parallel universes theory where like each universe was exactly the same up until the moment of the 2020 election, and then we see which of those universes Joe Biden wins in. Uh, that seems weird. Also, I think you have to make some assumptions about determinism, like what to say that it, I mean, this is philosophical here, but like, what's to say that everything isn't predetermined? So all of those universes would have the same. Anyway, it just becomes absurd, right? So rather than having to think about this in terms of relative frequencies, we can just say, well, an individual can have a degree of belief in something. The closer to one it is, that they think it's more often going to happen. The closer to zero is, the less often they think it's going to happen is. But as long as you assign those probabilities in a way that do not violate these rules, totally fine. You're allowed to do that. I don't want to go too far into this, but you could actually go so far to say is like, suppose two people have very different opinions about that degree of belief. That's also okay. And there's actually you could sort of like take that process and end up with so like maybe one person says Biden's 55% to win, another person says Biden's 45% to win. You could then do the math and come up with a fair bet for those two people to engage in, where they would both feel comfortable taking it. There's a way to derive the Bayesian degree of belief type things all through betting and gambling, but I'm not going to go down that route. Just to say that, as long as you don't break the rules of probability in expressing these degrees of beliefs in an event, you can totally do that, and you no longer have to appeal to these weird thought experiments about repeating events that frankly cannot be repeated. Flipping a coin, a lot of times, pretty easy. Rerunning an election that involved, 200 million people or whatever it was, that's a weird thought experiment. You can't really do that. So there are times where it just makes more sense to think this way. Now, where this gets even more interesting is that degree of belief is often expressed in terms of a distribution of possible parameter values. In this case, like the probability that Biden got elected president or whatever. So in frequentist statistics, you cannot make probability statements about parameters because they're fixed. They're not random. In Bayesianism, go crazy. You can literally specify a distribution of a parameter that states your degree of belief that that parameter takes certain values. And that's kind of what we'll talk about in an example a little bit. And then so the way we do inference then is based on that distribution of that parameter. But the very clever thing here is what we'll see is that the way Bayesian statistics works is you start off with a belief, but then you observe data and you use essentially Bayes' theorem to combine those things to update your belief based on the data you saw. So in a lot of ways, I think Bayesian thinking is really what people naturally do. That's why some of the weird things in frequentist statistics often just don't jive with people when they first see it because it doesn't make sense. But the Bayesian way of doing things, I think, is very intuitive. The trouble is, as we'll see, the mathematics gets very difficult very quickly. That is the mathematics with the computation. And at some point, the line blurs there. But I think that's a very, what's the word I'm looking for here? Intuitive way of thinking. Well, state my belief about something, go out and get some data on it, update my thinking on the thing, incorporating my previous belief and the data. And we'll even see that this Bayesian way of doing statistics, like it sort of auto balances itself too, where it takes into account how strong your belief was versus how much data you saw, and it uses that when it combines that to update your belief. It's really quite intuitive when you get into it, and that's so I should say that Bayesian statistics is an entire field. You could take many dedicated courses on it. I'm just going to try to convey this main idea of this: you state a belief, you see some data, we update that belief. That's what I'm going to try to get across here. Okay, so again, Bayesian statistics sort of implies that we're going to be using Bayes' theorem, and we are, but I just want to remind you that Bayes' theorem in and of itself does not mean you're doing Bayesian statistics. Everything we see here, this is just a slide we had discussed maybe in the first or second week of class, This can all be derived from those 3 rules we set out for probability. There's nothing here having to do with interpretation or meaning of probability. This is simply following mathematical rules, and we arrive at this basically probability rule that we can use. And now we're going to use it heavily in Bayesian statistics, but nothing about Bayes' theorem is inherently Bayesian. It's just that Bayesians use it for a means to an end. Okay, so I sort of already mentioned the main idea, but I'm going to summarize it again here. So the first thing we're going to do is we're going to express our belief that something's going to happen. I should have like a running example here. What are we going to say? Actually, let's return to the coin example, because this is the canonical example, right? So like we're interested in the parameter probability that I flip it and it comes up heads, right? So I think if you think about this, right? Actually, I'll draw a little picture here. So here's 0 and here's 1, and we'll call this P. So obviously, because of the rules of probability that both frequentists and Bayesians have to follow and agree on, the probability that it comes up heads has to be between 0 and 1. Now, as a human who has been alive for some number of years and interacted with some number of coins, by just simply looking at it, seeing a heads, seeing a tails, feeling the weight, without even flipping it, just based on those things, I kind of assume that I think it's going to be something close to 0.5, maybe, and this is not going to be at a scale, but let's just say something like this. That's not a normal distribution because it ends at 0 and 1, but like I have a strong belief that it's going to be something about 0.5, but I could be convinced otherwise. I should maybe have made this sharper at 0.5. You get the point, right? Like I assume it's 0.5, but I'm allowing for some possibility of other thing. So this is me expressing my belief through a probability distribution. So the next thing we do is we model the data using a likelihood. And essentially, we'll see that more mathematically in a while, but basically what we're saying is, a coin, we assume that the probability is constant. I'm going to assume that for this example. So if I flip this repeatedly, it kind of makes sense to model this with a Bernoulli distribution. So that's what we'll be doing there. So then what happens is the update step. So then what I'm going to do is update my belief to obtain something called the posterior distribution. So prior means pre, posterior means after. So what I'm going to do now is I'm going to collect some data. So I'm going to flip the coin a bunch of times. And let's just say for the sake of argument that I flip it, 100 times. And let's say like 90 out of 100 come up heads, right? So previously, I believed that this was probably a fair coin, but I saw a result where the data I saw puts the result here. So what we'll see is how to update my belief. So it would probably shift my belief, and this is not to scale at all. In the homework, you'll make some of these plots, but this is not to scale. But just to say that, like, after seeing that data, my updated belief should probably move closer to that. It's going to be somewhere between what I saw in data and what I previously believed. So that's what Bayesian thinking does. You state your belief, you run an experiment or collect some data, and then you update that belief. Again, I think that's really intuitive. Now we just need to sort of talk about the mathematics of that all a little bit. So how do we actually do these steps, not just me drawing pretty pictures that get you the intuitive idea? Okay, so I want to rewrite down Bayes' theorem. So in this example, or this statement, we're going to be considering a parameter theta and a single observation x. So this would be, the parameter here is p, the probability that I flip the coin that comes up heads. The observation is 1 flip. So in this new way that I've written down Bayes' theorem, which we've more or less seen before, we can give all these things names. So here is the prior distribution. So this would be what I did on the previous slide, where I specify my belief about, what do I think the value of theta is as some distribution. So it'll either have a density or a PMF. I'm doing a continuous version of a parameter here, the way I've written this, but it could be either. So this here is the likelihood. And then what happens is we now get something. So now we get some distribution of theta given that data we saw. That's the posterior. So we had our initial distribution for theta, not having seen any data. And then we go through this process of obtaining some data, in this case, just one data point. And then we now get a new distribution for theta conditioned on that data. And that's our updated belief. This thing down here, we call this the normalizing constant. And that is basically just to keep the rules of probability in play, but we'll see in a little bit why we sometimes neglect to even talk about it. So often we'll be more in a situation like this, where we have, make myself a little bit smaller here. A situation like this where we have more than one observation, right? And sometimes we'll denote this as x to the n, and similarly here, this will be more like little x to the n. But so when we have this is where likelihood more comes into play. So if those are IID observations, I should note that, we can multiply each of their individual densities together and get the likelihood. And then Bayes' theorem looks like this thing at the bottom here, where this is representing the normalizing constant here. So now it says, okay, so here was our prior, here's our likelihood, taken together with the normalizing constant, we have our new distribution for theta given that data that we've seen. And a lot of times we sort of drop the normalizing constant and talk about it like this. So what we say is the posterior, symbol here means is proportional to, we say the likelihood times the prior. That's really hard to read. So again, this sort of is a very succinct way of saying that what we do in Bayesian statistics is we state our prior, which is our initial beliefs. We view some data and enter that into the model via the likelihood. Combine those two together, we get our new belief, which is the posterior, which is expressed as a new distribution for theta given the data that we saw. So once we have this posterior distribution, then we can do inferential things like we've been doing in frequentist land. For example, we might want so we have now a distribution for theta, but we might want a point estimate for theta. So what you can then do is use either the mean, median, mode, some measure of central tendency of that posterior distribution. So most commonly what we have here is the posterior mean. And you might already be thinking, this math is not fun. This is not, wow, I can't write. I can't erase. This is not fun math. And that's true. We're going to look at some situations where the math happens to be easy, but in practice, I'll say some things at the end of this video, like doing some of this is computationally intensive. And that's one of the reasons Bayesianism wasn't popular for a long time. But so this would be a natural point estimate. So you get that posterior distribution, and then you find its mean. So that's your point estimate for the parameter. But hey, if we have a distribution, I mean, one, that's already better. But if you have a distribution, it should be pretty easy to get an interval estimate for the parameter. So in particular, you need to find some A and B that satisfy these conditions. And then if you do that, well, the probability that theta is contained in this interval C that we've created is exactly 1 minus alpha. So then we say C is a 1 minus alpha. We're going to call this posterior interval. Now, you're probably thinking, hey, this sounds a lot like a confidence interval. It does, but it's not a confidence interval because it doesn't necessarily have the frequentist coverage properties that it's supposed to, although it might, you could evaluate that. But in particular, it also has a slightly different interpretation. We can say the probability that the parameters contained in this interval is some probability, because now we can make probability statements about parameters in Bayesian land. So We don't use the confidence interval nomenclature here because confidence intervals can't do that. So we call this a posterior interval instead. But ultimately, it's getting you an interval estimate for some quantity. Now, we're not going to dive into the details of doing, say, testing under Bayesian statistics, but I want to briefly mention that we can do some things that we would never do in frequentist world, which is, so that if you specify the hypotheses in terms of parameters, well, now we have distributions about parameters, so we could literally calculate the probability of the null hypothesis being true given the data that we saw, and vice versa with the alternative. That would be hearsay in frequentist world because, again, the parameters are fixed. You can't do anything distributionally with them. But in Bayesian world, we can do that because we can now consider distributions of parameters. There's a lot of practical considerations if you want to do Bayesian testing, but I just wanted to mention that we can now get probabilities of hypotheses, as weird as that sounds to someone who has only done frequentist statistics. Okay, that's a lot of information and a lot of talking about it in not concrete ways. So let's do an example that hopefully illustrates all the points we just said. So, because we're talking about coin flipping, obviously we're going to do a Bernoulli example. So, in this example, we're going to observe n flips of a coin, that is n Bernoulli random variables, assumed to have some fixed probability p for, say, success, turning up heads in a coin example. We're going to use a uniform prior distribution. So our prior belief for p is going to be, we assume any value between 0 and 1 to have equal probability. So it would just be a flat density between 0 and 1. Sometimes we refer to this as a flat prior. So it's kind of, we're sort of, well, by using by using a flat prior, we're sort of saying, hey, we don't want to, influence this too much. We don't have a strong prior opinion. But we'll see how to modify that in a second. Okay, so what we want to do then is, with that information, we want to figure out how we would update our belief given that data and that prior. So we need to obtain the posterior distribution for p given the data, which, like we said, is proportional to prior times likelihood or likelihood times prior, either way. And we end up with this statement here, which I'm going to note here. This is a valid likelihood. Because, the prior was 1, so that doesn't affect anything. So this is just the likelihood that we're staring at. Oh, by the way, S is the sum of the xi. But this is not a valid density. So we're going to need to come back and fix that. So we would need to obtain that normalizing constant. But a theme here is going to be that I don't want to do any integration. But so what I'm going to do real quick is a step that is not going to make sense yet, but it will in a second. I'm going to rewrite it like this, which is equivalent, but just slightly different. So this should be n minus s plus 1, that whole thing minus 1. Okay, that's going to seem silly for a second. Bear with me. So now I want to recall some facts about a beta distribution. So this first line here in black, that is the PDF of a beta distribution. I also noted its mean because that'll be useful to us in a second. So what you might notice is in this sort of odd statement I rewrote here, if you sort of say, well, I'm going to consider s plus 1 to be alpha here, and then this n minus s plus 1 is this beta here, and then, well, if I do that, well, then this looks exactly like a beta distribution. So I just need to, match everything up correctly, and that's my that's 1 over the normalizing constant that I just need to add here, and that's what we've done here. So this is kind of the tricky way to figure out the actual posterior distribution without having to do any integration whatsoever. So sometimes we'll say, so P, given the data, we say that this follows a beta distribution where the first parameter is that s plus 1, and the second parameter is that n minus s plus 1. So then that allows us to do really nice things. Like if we wanted to get the posterior mean, which I'll denote like this, that would be alpha, which is s plus 1, over alpha plus beta, which is s plus 1 plus n minus s plus 1, which works out to be n plus 2. So this could be a point estimate, and this is the posterior mean. Okay. And oh yeah, and I was gonna say we did not do any integration. No integration. Which makes me happy because I'm bad at integration. Couple things I want to note. If you think about using a uniform prior here, while that does sort of say, hey, we don't have any strong prior belief about where the true value is, the prior mean would be 1/2. And if you sort of look at this, the usual MLE here would have been something like this, right? But so this posterior mean is kind of biased, and it's biased towards a value of 1/2, which that's the influence of the prior belief there. And we're going to circle back to that more specifically in a second, but I just want to get you to start thinking about that. So now what I want to do is sort of redo this example, but do it a bit more generically. So now, instead of a uniform prior, I want to consider an arbitrary beta prior. So a beta distribution, recall, it considers values. It's a density that's valid over 0, 1. Actually, the uniform that we looked at is a subset of it, but you could get all sorts of shapes. But depending on the alpha and beta you pick, you can specify all different priors. You get something that looks like this. You could get, a uniform like this. You could get something like this, and so on and so forth. So depending on how we specify alpha and beta with a prior, that sort of gives us a different distribution for our prior belief, but we're going to do it in general for any alpha beta. So this is the likelihood up here. This is the prior. And without doing the math, we might ask you to do it once on the homework. It turns out that the posterior is this. Posterior. Okay. And you might notice that both the prior and the posterior are both a beta distribution. That's because when the likelihood's Bernoulli and we use a beta prior, that's something called a conjugate prior. Conjugate prior. That's a bad looking conjugate prior. Okay. So what that means is there are certain combinations of prior plus likelihood distributions where it's just well known that the distribution that's going to pop out the other end is the same as the prior, just with different parameters. Actually, I forget. Is there a table of these in the book? I think there's not. Oh, is it in the back? No. Huh. It's not. So I will say that actually in the that big cheat sheet I have linked in the syllabus, there is a page in there. But this is something that you can just look up. So if you're dealing with a likelihood that is a well-known distribution like normal, Poisson, Bernoulli, whatever, and a prior that's a known distribution like beta, yada, 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 oftentimes there's probably a conjugacy thing there, and you can just look up what the posterior it is, and that posterior will be based on the parameters of, the posterior parameters will be based on the prior parameters plus the data that you saw. So that's a clever way to avoid these very nasty looking integrals that I don't want to do. Right. So, I should say here that the other way to do this, if you don't have conjugacy, you have some really nasty integrals that you kind of just can't do. So to deal with that, we move over to computation. And there's a whole chapter in our book about this, but there's entire courses dedicated to this. You can use Markov chain Monte Carlo methods to essentially numerically deal with those integrals. There are entire programming languages basically dedicated to doing that kind of work. For example, one's called Stan. It has bindings in both R and Python, but I digress. We're going to deal with conjugacy in this course just to drive the idea home. But so because of that conjugacy, we very quickly get the posterior distribution. So it's a beta with basically updated parameters. And so what I want to look at now is the posterior mean of that distribution. So I want to note that here I've written the prior mean. I should probably actually add the usual MLE would be something like this. And what I want to show you is that this posterior mean can be rewritten to be a function of the MLE and the prior mean. And recall, so the prior is only based on your prior belief, and the MLE is effectively only based on the data through the likelihood, right? And sort of what we see is we kind of have these constants out in front of those two different potential estimators that tell us how to blend them together to get the posterior. And if we look at this, there's actually some really clever things that are happening here. So suppose that we saw a lot of data. So n was really high. Well, if n is really high, then this coefficient here is going to be very big. And potentially, because of there's an n here but not on the top, this coefficient is going to be small. So what that means is as we get more and more data, the MLE sort of contributes more to the posterior mean than the prior mean. Conversely, if we have small n, this coefficient gets smaller and this one gets kind of bigger. Or also, I'm going to have you make pictures of this on the homework to really drive this home. With the way the beta works, if alpha and beta are big, that's kind of going to it's going to make it less variable and strengthen your prior belief, which would put more weight here. So that's kind of the really big idea. Like this expression here sort of almost encapsulates everything I want you to know about Bayesianism, which is that what it does is it's a clever way to combine what you already believe with what you see in the data. So yeah, all the problems on the homework are going to deal with conjugate cases like this, so you don't have to do any of the nasty integrals. You can just look up the conjugacy unless we ask you to sort of go through the tedious steps of deriving it. And then you're going to be asked to do things like sort of consider different priors with like the same resultant data and see how that update to the posterior works. So nothing too crazy or even that practical, but hopefully it really drives home the idea that the big idea in Bayesianism, which is that you take your belief, you see some data, you combine it through Bayes' theorem. Okay, so that's it. That's a very whirlwind overview of Bayesian statistics. Again, you could literally spend a lifetime studying Bayesian statistics. Folks do it, but this is just getting across the main idea to you. Okay, so as always, if you made it to the end of the video, good job, and I will see you in the next one.